Okay, welcome back everyone to another round of the Visual CS Plus Libraries video code reviews. Today we'll be looking at a PR implementing a CS Plus 23 feature called Invoke R. So let me go ahead and share my screen. There we go. And let me go ahead and turn off my video and incoming video. Okay. Okay, so the PR that we're going to be looking at is 2019 in the Microsoft STL repo. So let's take a look at that. And if you would like to know how I got to PR 2019 so fast there in the address bar, I have now documented that. If you go to the STL's wiki, let me show you that. Over in the custom auto links tab, or page. This explains how in our repo, you can cite bug numbers by just saying the name of the database and then dash and the number, which is quite useful. This is a GitHub feature that's enabled for pro and enterprise repos or accounts. And since it's sort of related, I also documented how you can customize your own browser. This is just a browser feature. To type in a keyword followed by a number, and then it will take you to a bug or a paper or whatever. This works in all the popular browsers I know of, and I recommend this if you're constantly looking up bugs in a GitHub repo or LVM or WG-21 papers. Quite useful. So we're looking at PR 2019. This is functional implement invoke R, contributed by SuperWig, who's implemented other features. And as usual, we track all papers with an issue. So this is the original issue that we filed right after it was voted into the standard. We actually do know a final value for the feature test macro here. And we can look at the paper as well. But first, let's get some background on what is an invoke and why would you want to invoke a thing? And then why would you want this invoke R? So let me bring up the standardies for this. So the backstory here, actually, my sketching out some code examples might be even better. So let's do that. Okay, we don't want that. Here we go. And I think we can make this a little bit bigger. Okay, so go back to the ancient world of CS Plus 98. You're implementing STL algorithms for the first time, and you end up saying, okay, I want to write generic functions that can be customized by the user. In the C world, they would think of that as a callback, focusing on the actual mechanics of, okay, I am a library function like qsort that's going to call back into the user code, sort of reversing the usual flow of control. In CS Plus, we usually don't think of callbacks. We think of, oh, I'm going to take a function object. And this is going to be something that happens to be given to me by the user, but it's going to customize the operations that I'm performing. And I usually default to something like less or equal to, but I'm not really interested in what the function, as the algorithm, I'm not really interested in what the function object performs. So I can accept whatever the user gives me as long as it follows certain rules. So the natural way to write that would be, and this is not necessarily 100% conforming to code, you've got some, I'll just say iterator, and then type name function object, being very verbose here. Maybe you return a size t, and you're called count, and you take an iter first, iter last, and then a function object f. And then you can say something like for iter I is first, I not equal last, plus psi. We would want an answer. Here I'm sort of implementing count very quickly. Size t, just n is fine. If, and so here's where we call back into the user code. We look at the provided object, or sorry, the element in the sequence. And then if the function object returns something that is true, we can increment the n that we get, and at the end we can return n. So unless I've made egregious mistakes here, this looks like a sort of naive implementation of the std count algorithm. But we needed a certain kind of syntax to call the function object. So we used parenthesis syntax. Now in C and C++, in C and C++, functions are not really first-class citizens. You can't pass them directly. What you can pass is function pointers. And it turns out that if you have a function pointer, the syntax of which is kind of obnoxious to declare, you can, I can go ahead and declare it. So if you said, we can extract it with the type def using the new syntax, function pointer, it could be a function returning bool and taking an int by value. So this type reads as inside out, a pointer to a function, taking an int and returning a bool. If you're used to the older type def syntax, it looks like this, which made sense back in the 70s. Function pointer, or so I am told, where it has to look like a declaration. So this reads the same way. Function pointer is a type that's a pointer to a function taking int and returning bool. It just has to be written inside out, so it looks really strange. The new using syntax generates the same kind of type def, but in a more readable manner, because this is what you would write if you were passing it directly, like to a template or something. So if you have a function pointer variable, like function pointer fp is the address of, something. In code below, you can call it by dereferencing the function and then applying it to some integer, and then this returns some, bool value like this. Going back to all the way back to C, Dennis M. Ritchie, who invented C, said, okay, most of the time I want the code that the programmer writes, and this is me sort of paraphrasing the rationale as I understand it. Most of the time, what the programmer writes should translate relatively directly to machine code. There's only a few places in C where code expands to something a bit bigger, like when you return a struct that will, or take a struct by value. I believe you can do that in C. That expands to a whole lot of, potentially copy instructions, but generally C doesn't like to expand a whole lot of code. There is like one kind of exception for a function pointer though. As I understand it, the philosophy here is DMR said, okay, if you're gonna be calling a function pointer, this is very useful. And the syntax, if you had like just FP directly calling 1729 and you have a function pointer followed by an open parenthesis, what could you possibly mean? But you want to dereference the function pointer and then call it with the argument. So I will automatically dereference just in the compiler any function pointer that I see called like a function. You don't need to write the star around it. That way you can call function pointers as if they were actual functions, and that's kind of nice. So this is like one of the few cases where C provides a little bit of syntactic sugar that it didn't really have to. Like you could imagine a world where just a direct call to function pointers was not permitted and you had to explicitly dereference them. So it's cool that C behaves that way, something I rarely say. And C++, of course, behaves the same way with function pointers for compatibility. And when C++ added operator overloading, this syntax can now invoke an operator paren. So you could have a struct function object with a constructor, maybe some data members, need a semicolon here, and then it could have a bool operator paren taking some int, let's say x, and then doing some cool thing like this, is x even. And the syntax function object applied to 1729 will now invoke this operator overload. So this is useful, and when designing the STL, I believe Alexander Stepanov and Lee and everybody who was involved in the design said, okay, we've got operator overloading. So this allows us to sort of accept both function pointers and function objects and actual functions, which will decay to function pointers when they're passed by value with parenthesis syntax. So the algorithm doesn't actually care what it's calling. Could be a function pointer, could be a function object. As long as it's callable with parenthesis syntax, you're good. And thus, CS+98 was standardized, and everybody was happy for like 2 years before everybody started working on Boost. So there are some limitations to this. If you have, maybe you have a range of elements that are themselves objects, and you would like to count how many of these, say they're animals, are cats, because it's got a bool is cat member function. So CS+98 actually does have pointers to member functions. This is syntax that looks very weird when everybody looks at it. If you have, let's see if I can get this right without actually compiling it. Say you have a struct animal, and it's going to have a member function bool is cat. Let's not even make it const because that's an additional source of complexity. By default, animals are false. Maybe this is virtual or something, or polymorphic class, and it's going to be overridden. I would have to make it virtual. But here's the sort of basics. You can get a pointer to member function, and the syntax for declaring that is possibly even more hideous than with function pointers. Using, and I usually think of these as PMFs, pointers to member functions. This would be like this, and taking nothing in this case. Yeah. So this type reads as PMF is a pointer to a member function of animal that takes nothing and returns bool. If this were const, then the type would go here. And then you can say, just as a variable or data member, you could say something like this is the address of animal is cat. You always have to say ampersand when you take the address of a member function, whereas with plain functions, it's optional. And then if you have an actual object of animal type, you could call the thing with this syntax. Let's see if I can get it right on the first try. A.star PMF called with nothing. Yeah, there's a special operator in CS+ that is only used with pointers to members. .star. It's not a dot and a star separately. It's actually .star the token. And you can say, hey, this object, instead of calling a specific member function on it, I want to call whatever PMF points to, give it no arguments, and then get its return value. So this could be decided at runtime. This can be quite useful. You could say, if some condition, then I would actually like to call animal, and then I would have to define this if I want to make this compile. Is this animal a dog? And then this call here will call whatever PMF has been assigned. So you get like an extra bit of indirection. This can be quite useful, but it needs different syntax. And there's also pointers to data members, which are probably even more obscure. They use similar syntax. They're really kind of offsets. The way the compiler implements them can be quite complicated, especially in multiple inheritance and virtual inheritance scenarios. If such thing sounds interesting, I recommend becoming a compiler developer. But I am lazy, and that sounds like work. So I'm a library developer. I'm going to get the compiler to do all that magic for me, and I just need to learn the strange syntax here. With this syntax, though, this presents a problem for the classic C++98 algorithm design. Because if I've got a range of animals and I want to count how many are cats, and I try to write, size, t, the number of kittens is, let's count from first to last. Maybe these are, iterators into a vector. I would love to just be able to say this and just pass an address to the isCat member function. This will not compile because even though, like, in some sense, it's obvious what I want to do, I cannot syntactically invoke a pointer to member function with parenthesis syntax on an object. I can't say f paren drfi here. It would need to look like, let me get this right, drfi is the object .star PMF, and then that whole thing has to be wrapped in parentheses, pretty sure, and then called. And that is not what the algorithm wants to do. So PMFs cannot be directly called with parenthesis syntax. You can write a lambda these days. A lambda is actually a little bit more friendly to the optimizer. It's also a little bit more verbose, but you have to know to do that, and it's still like a little bit of work. Or you could write a handwritten struct if you're going to be doing a lot of that, but you can't pass the PMF. So that's kind of sad. So as Boost and then the TR1 addition sort of DLC to the standard in 2005, and then finally CS+11 were developed, there is a sort of new technique for generalizing function objects into what the standard refers to as callable objects. So a function object is anything callable with parenthesis syntax. Like we saw f of drfi here. When I say of, I usually mean open paren. Whereas when the standard says callable object, this is a term of art. It means function object or a pointer to a member function or member data. Something that's callable in a generic sense. And this is powered by what was essentially exposition-only standardese in CS+ 11 through 14, if I've got my history correct. This was activated by std function, basically all the TR1 era stuff, std bind, and a few more. Std thread uses the invoke protocol. I'm probably forgetting a few more. And the idea is that these would use internal library machinery to accept pointers to members and have that work automatically. So let's see if I can get this correct for function. Again, I'm just sketching out code here so you can see. Imagine if I wanted a std function that is going to return a bool, and it is going to inspect, let's say it's a const animal ref. This is the syntax for having a polymorphic function object taking a const animal ref and returning a bool. This is using a function type, as an aside, that is a close relative of the pointer to function type down here, but is so strange that very few programmers ever see it until they start working with std function. And this actually does exist in C, but it's also very obscure. TR1 and CS+11 chose this because it's a way to encode a variable number of things into a single template argument. It's still sort of reasonable for std function because that parenthesis syntactically makes it look like it's going to be called. The same syntax was used in std result of with less than stellar results. Haha, pun. And now std invoke result has superseded std result of because it can use actual variadic templates. So that's a side there. So we've got the std function. We could give this a function object. We could initialize this with a pointer to a function, or we could give this a pointer to member function. So we could say, I would like to initialize you with animal is cat or is dog. And so this pointer to member function can be invoked on a const animal, and then it will return a bool. And std function will know through compile time internal machinery to expand to the .star PMF syntax. And yet the std function, I need to give this a name. Here, call this std function like this. Std function will know when it's actually called on an animal with its operator paren to expand to the .star. So this was sort of exposition-only library tech that needed to be implemented at great library implementer cost of sanity in CS+11 and 14. But it was so useful that in CS+17, it became available as a function that users can directly call. Arguably, that probably should have been the case in CS+11 and certainly 14, but better late than never. So now, this is accessible as a function called std invoke, provided by the functional header. And it will invoke a callable object. This is just what usage looks like, which could be, as I mentioned above, it could be a function object, a lambda, which is a function object, a pointer to member function, pointer to member data, and then some optional number of arguments. You could decide how many. Maybe there's no arguments, maybe there's one, maybe there's two, maybe there's infinity, hopefully not infinity. And then it'll return void or non-void depending on what the callable object does. And invoke will handle the metaprogramming of adapting the syntax. So as I like to say, this is kind of the standard library, the library standardese, sort of overruling the decision of core standardese. Core says you really need separate syntax to call function pointers, actual functions, function objects from the dot star and arrow star needed for pointers to member functions and pointers to member data. The library looks at that and says, but I want to call these things uniformly. So if the compiler and the language are not going to do that for me, well, fine, I'll make my own language. That's what Invoke is doing with all this metaprogramming. Invoke does a couple extra things. At this point, it would probably be hard to exactly put Invoke's machinery in the core language, although I continue to think that it should be done by the standards committee. In particular, the way it automatically dereferences smart pointers to objects and reference wrappers it would need extra wording. But the core language has shown recently that it can work with the library in cases like structured bindings. So I continue to hope that perhaps someday we will not need std invoke anymore, and we'll just be able to say with parenthesis syntax, hey, I'm going to call a callable object with arg1 and arg2, even if it is a pointer to member. But that day is not yet and does not appear to be the case for CS+23. So std invoke is what we got. It's also const expr. That took a while to achieve, but that is also the case. And so that's sort of the background to Invoke. I could show the standardies. The standardies for Invoke is pretty complicated. I think CPP reference, which is unofficial but extremely useful, may make it a little bit easier to understand. I can show you the standardies if I can find it. It's in General Utilities Library. It's in Function Objects. I believe it would be in Definitions. Yeah. So here are the standards terms of art. All these italicized terms. A callable type is a function object type or a pointer to member. Function object type is then defined to be things that are parentheses syntax. And then here is the, let me see if I can zoom this in, definition of what Invoke is. The standard is still following sort of the TR1 CS+11 era of specification, where it first defines a hypothetical imaginary exposition only function, which is written as capital italic invoke. And then in CS+17 and beyond, it goes and defines an actual std invoke. Probably it should be flipped around, but that would be editorially a headache, so that hasn't happened yet. There's a whole bunch of bullet points here. These are all the various metaprogramming special cases where it says std invoke is going to look at the callable object f and decide what syntax to expand to. So it's following a system of rules saying, okay, is f a pointer to member function? Is it a pointer to data member? Is it just a callable object? What arguments am I being given? Do I need to say .get to access a reference wrapper? Do I need to dereference it because I'm being called on a raw pointer or a smart pointer? But the overall effect is that Invoke will handle essentially anything that you throw at it as long as you're following the rules of what it can handle. And metaprogramming, which originally was a system of specializations and nowadays is a bunch of if const expr, will expand to all of this. So that's Invoke. I can show you the implementation real quick, although it is quite complicated before we get to the PR. I know this is a lot of background, but hopefully it is useful. As I'm looking this up, it's in, we actually implemented in type traits. I can just go there and maybe minimize this a little bit. Okay, let's go to type traits. Nope, I'm hitting the wrong key. There we go. It's also useful to know that in CS+20 ranges, range algorithms all use the Invoke protocol. So you can pass to ranges count a pointer to member function, and it will do the right thing because it's going to use Invoke internally. This was not extended to the classic STL algorithms, mostly for concerns around backwards compatibility, but also throughput. If we just started adding a whole bunch of metaprogramming and if const expr to existing algorithms that currently are always being given function objects, people would probably notice throughput regressions and complain that we're making their compile slower for no good reason. So the existing algorithms have not been changed there, but if you call the ranges algorithms, you get two syntactic convenience: one, not having to pass first and last separately, and two, the Invoke protocol. So let's see if we can actually find Invoke here. Yeah, so here is the user visible function, and then it's implemented with a whole bunch of stuff above. And this code looks horrible, and there's no getting around it. There's a whole lot of complexity to implement all that standardies. This is what your standard library maintainers are dealing with in order to provide good user experiences. It's got a bunch of struct specializations that will, or helper structs that will expand to the necessary call. So here you can see we have a helper struct that's going to invoke PMFs on pointers, or invoke pointers to member data on objects, and so forth. One final aside is that because we wrote this so long ago and then overhauled it, I did the overhaul and then it was later revised by Billy O'Neill. And now we're continuing to accept open source contributions that are further refining this machinery, including InvokeR. One interesting aside is that because we wrote this so long ago, this was back when MSVC was far more primitive and buggy than it is now. It's come such a long way. Early on, MSVC had extreme difficulty with the CS+11 feature expression sphenae, which is the ability to sort of speculatively compile and then back out of expressions if they turn out to be ill-formed in certain specific ways. Expression sphenae was so problematic at the time that we tried to avoid unnecessary usage of it in the STL whenever possible. So when I overhauled this to fix all the bugs, I avoided expression sphenae at every single place possible except for where it was actually needed as sort of the final call site. So this ended up being a lot of library code, which could have been less library code if we could use expression sphenae unrestricted. But it has had an unexpected benefit, which was further improved by Billy's overhaul. Because we use, originally it was, I believe, tag dispatch, now we use if constexpr to select the kind of invocation that we're going to perform, meaning parenthesis invocation or pointer to member function invocation and so forth. We don't actually ask the compiler to do the very difficult work of expression sphenae until it's absolutely necessary. We're doing very lightweight checks on, is this thing, pointer member function and so forth. And this ends up being very fast for throughput. I believe somebody did, outside of Microsoft, did an analysis, comparative analysis of the various STLs and their throughput for Invoke. And MSVC was, I believe, by far the fastest. And it's because MSVC, the compiler, used to be so buggy that we had to work around it. Nowadays, the compiler can handle expression sphenae quite robustly. I'm very glad to have put those buggy days behind us. But we've retained the Invoke throughput improvements because that's just how our code works. So it compiles fast, and it's pretty great unless you actually need to read through this stuff. And it's actually, once you're maintaining the library code all day, this is actually not so hard to read. There's a worse templated code out there, if you can believe it. Okay, so that's the rationale for the Invoke protocol, how it's used in the library, how it's increasingly used in ranges. Let's talk about Invoke R and then actually look at the PR. PR is actually relatively small once we understand the rationale. So Invoke will accept arbitrary stuff. In fact, it tries to reason about the arguments that it's being given as little as possible. It just inspects, are you a member function? What about the class to determine these relationships? But otherwise, it's perfectly forwarding stuff down. It's perfectly returning the value. Sometimes, though, you would like to coerce or convert the return type to something else. This is the case in the CS+11 bind, which I think Invoke R was influenced by. Let me open up VS Code and sketch that out. So bind, perhaps one of my least favorite library functions, but it's still there, it's still standard. You can say bind, callable, object, arg. You can give it placeholders. You can give it more placeholders, things like that. And it will bind some arguments now and then leave some open for later, so that this is very sketchy code. I think it would compile if all this stuff existed. Later on, you can call B with just two arguments, like 17 and 29, and it will fill in the blanks. So this would end up calling callable object using whatever generic syntax is necessary with arg1 followed by 17, the placeholder 1, followed by arg2, followed by the placeholder 29. So as an aside, I strongly discourage using bind in any new code. Do not use bind. It seems cool, especially when you learn about it. It's not. There's a whole bunch of reasons why it's a headache. I usually tell people to use standard library code. This is one of the few cases where I'm like, do not use the standard library here. Use lambdas instead of bind, please. But bind still exists. And one of the very obscure things it can do is you can actually give it an explicit return type. This comes from Boost and TR1. My vague understanding, I could be completely wrong here, is I believe that the bind R syntax was actually originally added to work around compiler deficiencies, because like as much as I complain about how difficult it was to work without expression speed A in like the say 2010-ish era, Boost was developed in like the early 2000s. Compilers were way more primitive back then, to the point where it's surprising that powerful things like bind and shared putter and all the other stuff we appreciate were developed. Boost developers just absolute heroes for developing all this stuff with tools back then. I think bindr actually existed to work around compiler bugs, but it can be useful too to say, hey, I know that this callable object is actually going to return, say, a long, but I would really like you to narrow that to an int, because that's what I want out. Or maybe it returns a short, and I would like you to widen it to an int before I go past something else. Maybe I'm passing it as a temporary, and I don't even have a chance to widen it as a named variable, something like that. So you could give an explicit return type to bind. This activates a certain overload that has the overload looks like template on type name R, and then the usual arguments for bind, return type bind. And so if you call bind angle bracket R, that ends up being used here. And this is overloaded with the other bind, and it all works out because the core language is complicated and the compiler devs are awesome and they manage to deal with all this complexity we throw at them. So bind can be given an explicit return type. And now invoke can too. Even outside of bind, we did need invoke, what we think of as invoke ret or invoke R functionality for std function. So std function, whose use I do encourage, as long as it's providing value and not unnecessary, because it does have space and time costs. If you have a function, and let's say that it returns something like a std string, and it takes who cares what the args are, f. Imagine that you initialize this with some my function. And imagine that my function looks like this: const char star. No, I called it my function. 10, and it returns something like this. N mod 2 is 0. Why even use an if statement? Then cats, otherwise dogs. Okay, so it's just going to return a string literal as a const char star. Now, and actually, let me, for even more hilarity, it can look like this. Okay, so if you're looking at the types here, you'll notice that the type of the argument and the return type differ. This function f says, I take an int and I return a std string. But internally, it's going to call my function. This actually will compile. It should compile without warnings or errors. What will happen is that at the top level, the actual usage of f, which could look like this, string val is f of, we'll say 10. This is going to be cats. So f is at the top level is going to be given an int. That int will be passed to my function and will be implicitly converted or widened to long. So that's safe. It's widening. Everything's happy. My function runs. It returns a const char star to the std function machinery. Std function then needs to convert that const char star to the std string that its interface has promised to return. So that will invoke std string's constructor, and you'll get a val out. So here the argument conversion sort of happen for free. That always has to happen. But the return type conversion, we need library machinery for that. In particular, this one kind of happens implicitly, but function also permits this. Function of void int f2 is my function. For things with side effects, you can say, hey, I'm going to take whatever arguments I take, and then I'm just going to drop the return value on the floor. This will accept anything that's callable with an int, and it's just going to discard the return type. Here's another case where the library wants to do something cool, regardless of what the core language wants to let us do. Core language says that types are technically not convertible to void. So if you have something like a void outer taking an int x and you say return inner x, where you've got a function that returns non-void, like this. This is a compiler error as far as the core language is concerned, because you're trying to return a non-void as a void. That's bad. You could do this if the inner function were void. That's permitted for genericity. But non-void to void, that looks like you're dropping something on the floor you shouldn't. So the core language says no. The standard library says, hey, that sounds good to me. So function and the invoke protocol has a special case saying, hey, you can just drop anything that's void on the floor. So we need library machinery to handle this return type conversion, including to void. Function has always needed this going back to CS+11, and bind has needed this. And now this is finally in CS+23 being granted to users in the form of invoke R. So now users who need something like function or stood function, in particular this return type conversion when doing this generic invoke, can now get it. Okay, so that is all the exposition we need to actually start looking at this PR. So we've got the paper. We could look at the actual standard where it's been applied. That would give us the value of the feature test macro. I actually should do that. So why did I close the standard? I don't know. The feature test macro we're looking for is cpp lib invoke R. I believe it should be 2021-06, since I think that's the one we've voted in. cpp lib invoke R. We could also look at SD6 if it has already been updated. Yep, that looks like 2021-06, but let's make ultra sure. We've got one macro for the original edition of invoke, and then a second one for invoke R. Yep, so the value should be 2021-06. Got it. Since we're going to accept this pretty soon, I'm not going to bother updating the issue right now. I might do that later. Okay, so let's look at the wording. This is going to talk about the rationale, but I've already given that exposition. So the actual standardese is we're adding a new overload. It has an additional R. So here, invoke is not doing the funny thing that bind did, where it overloaded bind and bind angle bracket R with literally the same name. Here, if you want the one with the return type, you actually have to say invoke underscore R. R is the first type, and then F and args. It's also const expr, returns R specifically. It has a conditional no accept. It uses the type trait that we previously implemented is no throw invocable RV. So it's going to essentially have the same no acceptness as the actual invocation. Invoke is now constrained to work only when, okay, this is already implied. So this is just a wording cleanup, no extra stuff to do there. Here's the definition of the new function. It's got the same sort of constraint that's also implied by the invoke. Oh, I see. So this constraint is actually necessary. The old invoke, its return type was specified as invoke result T, which is specified to sphen away if the thing is not actually invocable. So this says invoke should also sphen away. Invoke R has an explicit return type, R. That's its whole purpose for being. So we need to give it a constraint that it should compile only when the thing is actually invocable with the arguments and with the return type. So I know that was a lot of words. This my function is invocable R with the argument int and the return type string, string. It's also invocable R with the argument int and the return type void, but it's not invocable with the argument int and a return type of double. That conversion will totally not compile. You can't convert const char star to double. So this says invoke R should sphen away in that case. And then if it is allowed by the constraint, it's going to hook into the existing imaginary invoke. We already have this machinery in the library, perfectly forward stuff. So it's really just adding one function, doing what we already have in the library. But we got to make sure that we've got this constraint, that we get the return type right. We've got the feature test macro and the conditional no accept and const expr, and then of course test coverage. Okay, so that's the issue. Let's actually look at SuperWixPR, 42 minutes in. Okay, so let's alt click. Okay, we got feature test macro. We're adding a new test. We're updating LiveScore and functional. That all looks good at a first glance. Let's see the new paper. So let's always double check the paper number. I've seen way too many digit transpositions over the years. This all looks correct. We are mentioning this in the 23 section. I don't even need to expand. I can see this is the 23 section for removing garbage collection and range constructor for string view. I got those right. Okay, so the new paper is being mentioned here. It's in sorted order. Perfect. We've got a new feature test macro in the CXX23 block. It is also in sorted order. The spelling is correct. CPP lib invoke R. The value is 2021-06L as specified by the working paper. That looks awesome. Paper cited, feature test macro. Okay. iVal's core is good. Feature test macro test should have the same thing. It's guarded by if underscore has CXX23. Every mention is updated to say invoke R. Every macro says 2021-06L. It is in overall sorted order after invoke, but before is aggregate. So that's great. We're adding a new test. The test, this is one we always have to look out for because the GitHub machinery doesn't care if a test is mentioned here, it'll be run. But our internal test machinery, which we still have for the time moment, does need test to be mentioned. So the new test is being mentioned. Let's make sure the paper number is right, 2136R3. Yep, that's correct. Let's double check for typos. Yep, that's good. And it's being added in sorted order, 2136 before 2162. Okay, new test is good. We're adding a test list. I'm doing all the easy stuff first. We got a copyright license banner. We're going to use the usual latest matrix because this is a CS+ latest or 23 feature. But we don't need to use concepts here or exclude CLR or any of that stuff. So we call this the usual matrix of compiler options in our test machinery. Okay, so let's actually look at the product code, only 16 lines before the test code. Okay, so first question runs through my mind is this is being added to functional. Invoke itself lives in type traits. This is because it's used way throughout the standard library, including in the type traits is invocable R and his invocable RV. So because we need it so widely, type traits was the most convenient place for us to centralize it. However, invoke R is actually a leaf function. Nobody directly calls this. We're still using the internal machinery for std function. That's necessary because std function is a CS+11 thing, or CS+14, which is our lowest supported standard. It needs the capital invoke R machinery, which is not available in CS+23 mode. So none of that existing code can change or actually even take advantage of invoke R. This is purely being added for users. Perhaps in the far future, when CXX23 becomes our lowest supported standard in 2077 or something, we would be able to drop that internal machinery. But until then, we need to provide it for users only. So adding to functional seems right. Users might be a little confused if they drag in invoke but not invoke R from type traits, but that's sort of unavoidable. And this definitely is the best for throughput to provide it in the most leaf header possible. So that looks good. Now, question, where in the header is it being added? Looks like SuperWig is just adding it to the top as soon as we open up std begin, but before we define various structs. This seems fine. We have a general policy, just sort of a style convention in the library to define stuff in standard declaration order. I'm not actually even sure where this was added in functional. Let's see if that's following. If it is, great. If it's not, I'm not going to care too much about it. Let's look at the synopsis. So probably in function objects. Go. You would think that the synopses would be called out at the top level in the bookmarks, but no. Okay, so functional synopsis actually begins with invoke and invoke R. So putting it at the very top follows standard declaration order. So SuperWig is doing absolutely the right thing there instead of appending it at the bottom. So that is good. This convention is helpful because when you're auditing code in the header, in the actual implementation versus the standard, if stuff follows the same order, it's quite convenient. Especially when reviewing large PRs or auditing later changes, because who knows how this is going to evolve in CS+26 and beyond. So we certainly weren't disciplined about this long ago, but we are increasingly so. Casey Carter loves following this convention. I think he was the one who pushed for us to start doing this, and it is greatly appreciated. So I'm trying to uphold that whenever possible. Okay, so this is my sketches. Let's go look at the PR. So the order is good. It occurs at the top. Here we go. Okay. So let's see. Can I? Oh, I wasn't even at 125 zoom. Let's zoom in a little bit. Okay, so the guard, we're within stood. It needs to be pound if underscore has CXX23. We got a matching comment underscore CXX23. Here I'm looking for missing underscores, making sure we test this with if and not if-def, because this is a always 1 or 0 macro. We've got a what we call a shouty comment banner function template invoke R. Okay, I'm reading a bit ahead, which is why I'm pausing, because I've seen an issue. Okay, function template invoke R. So the reason why I paused is I saw cling format off, and my brain was like, wait, why are we turning cling format off here? And the reason why is we've got this requires. Cling format 11 doesn't really do well with concepts. So we conventionally turn cling format off when we're about to emit a concept. So this is emitting the constraint that is specified by the standard. However, we could implement this with SVNA, the usual enable if machinery that we have everywhere else. Our current convention, the reason why this is an issue, even in CXX23, is we have one front end. It's the EDG front end used for IntelliSense that currently does not support concepts fully. It supports it for IntelliSense, but for our test machinery, which actually needs to instantiate stuff, it's currently disabled. They're working through all the issues that the STL has found. So for the time being, our test coverage does not activate, or no, our product code actually does not activate concepts for EDG. So our convention is we avoid using concepts unless it's really required by the standard. Cases like that are ranges, which depend so heavily on concepts. I believe stood format, because it uses ranges, gets to use concepts. But if something merely needs to SVNA, we currently use enable if, even if it's CS plus 20 or 23 code. We've got tracking issues for when all the bugs have been fixed to go unconditionally use concepts and remove the pound if def CPP lib concepts guards. So in this case, the original invoke certainly does not need concepts. I believe that this one should probably do the same, even if the test code happens to be working. It is just not consistent with our current convention. So I'll add a comment here. This is using concepts, but not guarded by CP lib concepts, which could pose problems for EDG. I believe SuperWig actually knows about that tracking issue. We conventionally avoid using concepts, and we've had to rework code in at least Chrono, and I think one other case where we were using concepts, and it was definitely more convenient because it's a good feature. We had to use slightly more verbose SVNA code just to completely avoid any trace of code that could cause problems for all of our front ends, supported front ends. We conventionally avoid using concepts except when absolutely required. I was going to put a comment here. Even in CS plus 2023 mode, except when absolutely required, for example, in ranges. Even though this doesn't seem to be causing issues in the test coverage, where usual latest matrix list has BE, that's the option, undocumented option that activates the EDG front end configurations. I believe that we should continue to follow the convention here of using enable if T instead of requires. We have a tracking issue that will then clean this back up, or then change this back to requires in the future. Okay. This is using concepts, but not guarded by double underscore CPLib concepts, which could pose problems for E2G. We conventionally avoid using concepts, even in CS plus 2023 mode, except when absolutely required for example ranges. Even though this doesn't seem to be causing issues in the test coverage where usually AGIS matrix list has BE configurations, I believe we should continue to follow the convention here of using enable if T instead of requires. We have a tracking issue that will then change this back to requires in the future. Okay. And it occurs to me that at that point, we should also remove the claim format off. This should also allow Clang format to be enabled for this code. Okay. Yeah, this will just give us more confidence in our test coverage and avoid triggering compiler bugs, and actually paradoxically making it harder to find and fix all the issues that CPLib concepts is revealing. Okay, so ignoring that, that was the constraint here, so that's good. Once it's phrased properly, it needs to be const expert. It needs to be conditionally no accept. So let's look at the implementation. Okay, so we got template on class underscore capital result type, class underscore callable, class dot underscore types. We got the constraint. The constraint is itself correct, is invocable RV, and give it result type callable types. Very nice. This is now just variadic flat list, not that weird parenthesis syntax that Resultive used to use. Okay. Next, so before we get to the const expert, invoke R here is being marked as no discard. I believe that this is incorrect. Although we love no discard in the standard library, we got 4,000 occurrences of this. It's by far our favorite attribute. Invoke R, the callable object, we don't know what it does. It could definitely be called for its side effects. But actually, let me think. Ooh, this is a very unusual case. Invoke certainly can't be no discard. With invoke, because you could just say invoke some PMF has side effects, then you drop the return value on the floor. Invoke R though, if you're so concerned about the return type to explicitly pass it with angle brackets, and then you drop it on the floor, that is extremely suspicious. That seems wrong. If you pass void, then the compiler should just ignore no discard on void, and because it's a template, you should hopefully not even get a warning that, oh, no discard on void's bad. Okay, this is actually correct. I was wrong. SuperWig is right. This thing should totally be no discard because it makes no sense to pass a type and then just drop it on the floor, even if the callable object has side effects. Because why shouldn't it just be plain invoke or invoke void? If you want to drop it on the floor, you should say invoke void rather than carefully crafting an R that should just be void. Okay, so it's no discard. I don't think that needs a comment. It sort of self-explaining once you realize it's an issue. Okay, it's const expert is required by the standard. Result type invoke R takes callable ref underscore obj types ref dot underscore kept args. Can't be const, it's not a member function. It's conditionally no accept with is no throw invocable RV result type callable types. That activates a whole bunch of machinery that's been extensively tested, so it's good. And then here's that bit where the library says, hey, core language, I know better than you do. You should totally be able to convert stuff to void. So if the result type is void v, this will catch CV qualified void, which is desired here. I know this because all of the primary type traits, the type traits for primary type categories, like are you void? Are you integral? Are you floating point? Are you null putter t? All of those ignore top level CV qualifiers. So this will be true for const void, volatile void, and so forth. All of those we want to call std invoke by std forwarding the callable obj and std forwarding types args dot, but we want to cast it to void in that case. Even if invoke returns non-void. Otherwise, we should just return it. And I believe the standard depicts an implicit return. No. Okay. So that's very interesting. The standard depicts the invoke angle bracket R. Do we, I guess we implicitly convert internally. So what I'm trying to match here is this is not what I think of as punching through to the underlying underscore capital invoke ret machinery. This is calling std invoke and then implicitly converting it. We need to make sure that this is equivalent to the invoke capital R once the void bit has been handled. I think that's the case, but let's double check. Aside from that, code looks good. We turn Clang format back on. We've screwed that up a bunch, so I always like to check that the on is there and then close the end of. Okay, so let's take a brief detour and look at invoke ret. You would think I would know this because I wrote it, but it was years ago. Let me minimize a bit. We have a 120 column policy, which works nice on a large monitor, not quite on this portable device. Okay, so the invoke ret machinery, I believe I called it invoke or invoker ret. Nope. Nope. Where did I put it? Std function uses it. I could look that up pretty easy. Functional. Class function. Function. Here we go. Oh, and then the actual base. We've got the small functor optimization. At some point, we're actually going to invoke the thing. Must have skipped it. Oh, it's the do call. Okay, it's sorry. It's implemented by the func-impl, which is a little bit below. Get function impl. Did I just skip over it real quick? This is just computing the type. Let's reset alloc. This is the func class. Ah, here it is. Do call. Okay, invoker ret. That's what I was thinking of. Where did I put this? Oh, it's in functional. It's not in type traits. So that's why, because it's only needed by invoke. Ah, and look, my comment. Helper to give invoke an explicit return type avoids undesirable expression screening. Whoa, I don't want to scroll. I just missed it. Invoke ret. Invoker ret. Sorry. Okay, it's a struct. Here we specialized the struct on void or non-void because at the time I did not have if const expert. It's got some unforced stuff. This is to handle bind, sometimes not using that R and sometimes using R. Okay, so if we are void, we just drop it on the floor. This is like the void cast. If you are non-void, but you actually do, if you're not this unforced internal tag types, you actually do need to convert to R. We just return std invoke. Okay, so this is good. This is the bit that I wanted to check. We call std invoke. This looks exactly like what SuperWig is doing, perfectly forwarding stuff. And then at Rx, we just implicitly convert. There's no static cast. There's no other stuff. We got conditional no except, and that's it. So this is exactly imitating invoke R, but is not using the invoker ret machinery. The there's not even really, and I'm thinking, would it be an advantage since we are actually in or would be in functional if we moved the new code below? Would it be an advantage to use invoker ret? And the answer is no. We would have to specialize a struct. We'd have to call this thing, and in the end, we would be calling std invoke anyways. So we'd be adding an extra layer or two of instantiations for no benefit whatsoever. The if const expert is strictly better than what we're doing here. So rather than trying to use the existing code and actually making things worse, writing new calls to std invoke is absolutely the right thing to do and results in the least maintenance. Just a bit of one-time verification that this is exactly corresponding to what we got. So that all looks good. Only issue I see is the concepts. I can't think of any other way this is going to break. Okay. Let's take a look at test coverage. So in the comments to this issue, I believe SuperWig asked, hey, should we go exhaustively test like every callable object and all the different ways that this can be stressed? And because this is implemented in a nicely layered fashion where invoke R calls std invoke to do the heavy lifting of dispatching on PMFs and whatever, if we have confidence that std invoke works because we've got extensive test coverage, we don't need to replicate that here. And we don't even really need to focus on, okay, are we forwarding this stuff? Because we can just see in the code that we're forwarding. We need to focus on the conditional no except the const expertness, do you handle void correctly? Are you performing the conversion correctly? All the extra stuff that's being added as a layer on top. But other than that, the test can be quite simple and not have to go, exhaustively test every possible, const volatile, ref qualify, pointer to member function that we test elsewhere in the STL. Okay. So 82 lines test code. I don't want to add a comment yet. Okay, so we start with our copyright license banner. Always need that. We're going to C assert. We need to test functional where the stuff is, and type traits because everybody needs type traits. I'm just scrolling down to make sure we're not using anything else. We got invoke R. We got is same v. More invoke. Yep, that's also functional. Yep. Okay, so all the headers look good. Using namespace stood. Okay, so now there's a comment transition devcom blah. This is our way of saying we are affected by a compiler bug. So let's look up what devcom so-and-so is. Cool, SuperWig has reported a bug to the compiler. Stood invoke with a const expr function is falsely no except with /permissive. Believe this is the issue where the standard originally said, hey, if you're const expr, of course you can't throw exceptions. And that was later changed, but permissive is still doing the old behavior, even though strict mode permissive minus is working. So there's some question about, can we repro it? I think he followed up. Yep. Okay, so it's being investigated. So a compiler dev will look at this. So that's why we need to detect permissiveness in our test configurations, because we test both permissive and strict mode. There's no macro by design to detect permissiveness, but when we need to, we can just query it the hard way by writing code that's sensitive to the difference. So that's what this stuff is doing. I pointed SuperWig to this, or we do it elsewhere in the STL. This is just looking at the rule, does unqualified name lookup reach into dependent base classes? If this returns true, then we're in permissive mode. If not, we are in strict mode. So this code is exactly copy-pasted from elsewhere. It looks right. It's not really super critical if, like, the spacing is slightly off. So I'm not even going to do my usual trick of let's copy this and the original code into VS Code and then diff them. This looks good to me. Then we got some helper functions. These are const expr, take int, return int. We got square and square no except. Okay. We have a struct with a data member initializer int and 0. This member function is non-const and returns reference to guts and is const expr. We have a stylistic convention that we never call functions foo. It's not forbidden, but we just prefer to avoid it. There should be anything else like meow. We conventionally avoid naming variables, functions, etc. Foo. It's not outright forbidden by. I won't get into the policy details. So this should be any other name. Like meow. So it doesn't have to be cat face. Okay, conventionally avoid should be any other name. Yep. Okay. Reason for that, I guess I can explain the background there. Reason for that is that although foo is completely innocent, and so are foo and bar, together they can sound bad. So there's been a policy to avoid usage of it. The policy's actually been less, it's been less strict now than it is in the past, but it's just easier for us to completely avoid any occurrences, and cat noises are funnier, so I like meow. Okay. So is our value. This is overloaded on constant ref and int ref. Turn false, turn true. Okay. So now we've got test invoke R. This is a const expr function because we're going to use this for both runtime and compile time. So let's see, what test coverage do I want to see? We want the conditional no except. We're seeing that we are going to have the const expr coverage, and we want to look real closely at the conversions because that's what's being added, and also void. If we've got all that test coverage, then I'm happy with everything else, all the PMF stuff, all the forwarding stuff. It's really difficult to get that wrong. Okay, so we're going to invoke square, which takes int, returns int, and try to widen it to long. That's going to be an auto. Make sure we get 9 out, and make sure that the decal type is long. This is good, except for the convention we have. We never say long int. We only say long because it's verbose. In product and test code, we conventionally never say long int. Instead, it's always long. Occurs below. There is kind of a rationale there that it's unnecessary verbosity, and it's a little bit confusing to just be scanning and seeing int and then wait, oh no, it's long. We also never say signed unnecessary. We never say signed unnecessarily. We'll just say short rather than signed short. Of course, we say signed care because that is a distinct type. The one exception is that we don't take advantage of the standards rule that unsigned is by itself a type. We consider unsigned to be a modifier, so we will say unsigned int, even though you could get away with plain unsigned. It makes sense to me, if that helps. But it is our convention, and we are big on following convention, so all the code looks the same. And weird code will jump out at us. Okay, so long. Okay, so this is testing widening. That's good. We should also be looking at void, and I do see some void down there, so that's next. Now we are going to test, instead of a function, a lambda. This is a lambda that is specifically returning int and is going to be widened to double. Okay. This is a little bit more verbose than necessary. Like the arrow int here is not technically necessary because 5 is int. However, I think it's probably, and I'm suspecting it's the intent, it's useful to be really explicit, saying, I really care that this lambda returns int. I want you to notice that it's returning int and that we're going to convert it to double. That's why we need these parentheses here, because we got that explicit return type. This is good. I think the code would be more confusing if we just said return 5. So we widen int to double. We assert that v2 is equal to 5. This is actually comparing a double to the integer 5, and yeah, that's going to work. The 5 will be converted to double. We're not really concerned about the values, so saying like 5.0 here wouldn't really buy anything. Because we've got the static assert here that v2 is specifically double, so that we do get a double out. That looks good. Again, we're converting the return type, just as int was converted to long, we're converting into double here, and now we're using a lambda with parenthesis syntax. It's a different kind of function object. And then he's got another test that if you invoke R square with 1, but then drop it on the floor with void, that it is void. This is good. Technically, this test is a little bit less specific than necessary or than possible. This would accept const void, but of course, we're not going to like add const to return type for no reason. So like is same v void as this stuff, that would be overkill. If there were any question of a const void sneaking in there, I would say, yeah, let's use is same v, but since there's not, I think that is fine. Now we've got transition. Is this the same bug number? Yeah, same bug number. Okay, now that I've said it, I'm a little paranoid about typos. Okay, it is actually the same number that's been mentioned. Okay, so we need to check okay, we've looked at the return type widening. Narrowing would trigger compiler warnings. So there's no real need to test that because we know the conversion happening is implicit. So that's fine. But we do want to look at the no except. So let's make sure that if we invoke, okay, square is not no except, but square no except is. And it's being marked as const expr here. Okay. And we need, really, these should just be false all the time, but if we're in permissive mode, the compiler will wrongly report true. So that's why we're asking, is it equal to permissive? It's been marked as transition, so when the compiler bug is fixed, we'll go back here and fix this up. Okay, so he's testing both invoke R and classic invoke to make sure that they have the same no except behavior. This is good. Now I'm thinking that there is actually one corner case that we should maybe test. I'll mention that in a second. Okay, so invoke R int square 3. Yeah, honestly, these repeated messages I think aren't really useful. They could just be terse stack assert where we just provide the condition. I'm okay with it. This is this is a stylistic preference that I don't think we need to be globally consistent about, and it is consistent within this file. So I'm trying to avoid too many nitpicky comments that don't matter. Personally, I probably would just make a terse stack assert, but this is fine. This saying if this fails, invoke R int square 3 is no except, but it shouldn't be. It's a little bit. I've always found it, and maybe it's a little bit confusing to say static assert, bad thing happened. Usually I like to phrase the message in terms of static assert. Good thing should have happened or should happen. But it's not really confusing, so I think this is fine. Same for invoke. Just looking for copy paste errors. And then if no except is part of the type system, that's an if def. Looking at the core language feature, yep. Look at square no except, it should be, but if it's not, we saw that it isn't no except. Okay, that's all good. Technically, we went 2 lines here. This really should be commented. This should probably be commented according to our current, albeit not totally rigorous conventions. We like commenting preprocessor conditionals to avoid getting confused about what block we're in when the code inside expands during maintenance or if additional conditionals appear. This should probably be commented according to our current, albeit not totally rigorous convention. We do have a tracking issue to decide something there. Okay, thing. If we invoke a pointer to member data thing n on the thing, but then drop it on the floor with invoke R as void, that should not emit a no discard warning. And we do compile with WX, that's good. I like that, that's great test coverage. Then if you invoke the, oh, this is the reference to guts. Yeah, reference to guts. If you invoke that member function on thing, this is classic invoke, you should not be an R value. This could have been written as a static assert decal type. This runtime assert is doing this overload resolution at compile time. Or sorry, it's the overload resolution happens at compile time, but then the assert is runtime. In the end, though, we are context exploring this. This is essentially stylistic. It's providing sufficient test coverage. I'm fine with this. I guess the alternative would be, this is actually a little, I think I see why this is written. It's a little bit annoying to detect, are you an R value reference or are you an L value reference, or just like, or sorry, are you an L value reference versus are you an R value reference or are you object type? I guess that would be is L value reference versus not is L value reference. Or just not is reference if you know that the thing you're looking at is a PR value. It could be written that way. That would allow us to get rid of the is R value function. I think I'll mention that as a suggestion. I think it might be clearer. I don't see the value that is R value is providing now that I'm looking and staring at this. Okay, so this is verifying that plain invoke. Okay, I really like this test though. Plain invoke on this function returning a reference should return the L value reference unmodified through decal type. But if you specifically say, hey, I know you return an int ref, but I'd like to return an int PR value, we should get a PR value out. It should not be a reference at all. So here this is only looking at is R value, but looking at decal type, you could say that the decal type is exactly int. And here you could say, actually, is saying v would be fine. Here you could say that the decal type is exactly int ref. I think I might like that better than is our value. I'll recommend that. Let's see. Suggestion. This is a great test examining the return type when the conversion is as minimal as from, wow, this is terrible grammar. Examine the return type with a minimal conversion from int ref, don't know, there we go, try all the characters, to int. However, I think that the is R value machinery followed by a runtime assert, albeit later static asserted with the context per function, is whoa, what? Oh, I clicked and there we go. Is less specific than possible. I think it would be, let's express some hesitancy, unless I'm missing something. I think it would be clearer to drop is our value, and instead static assert that the decal type of these invocations is same v as, let's see, the first one would be int ref for the former and int for the latter. Okay. Yeah, basically we trust decal type to do the right thing. So directly examining that should be sufficient. Okay, suggestion, this is a great test examining the return type with a minimal conversion from int ref to int. However, I think that the is R value machinery followed by a runtime assert, albeit later static asserted with the context per function, is less specific than possible. Unless I'm missing something, I think it'd be clearer to drop is R value. And instead of static assert that the decal type of these invocations is same v as int ref for the former, yep, and int for the latter, yep. Okay, turn true. And then we, oh, I should add a comment. Then we finish off with just call the function to get the runtime static assert function, or sorry, call the function to get the runtime assert functionality, and then static assert the context per function to test all this stuff in compile time. So it's sort of dual mode. I think that's good. Okay, so did we test everything here? We've got actually no coverage of PMFs, PMDs, but I convinced myself that that's fine. Actually, no, we've got PMFs, PMDs. Sorry, we got them down here, so that's good. We got got functions, we got lambdas, we got conversions from int to long and int to double. We got conversions to void. We've got exercising the is, the if is void v internally, if context for is void v. We've got a test for the no discard warning. This is great. We've got tests for the conditional no accept. Oh, the thing that occurred to me that I mentioned earlier was this is not covering whether the conversion is no accept. And this is, it's possible for the code to get this wrong because it's the difference between is no throw invocable and is no throw invocable R. So this type trait only looks at what would happen if I called the callable object F with the args. this type trait looks at that and asks, okay, and then what if I converted its return type, whatever it may be, to R? Maybe that will throw. For example, f could be a no except function returning const char star. But if we then attempt to convert that to a std string's constructor can totally throw as it allocates memory. So that would end up being false. I think we should have a test coverage of that just because although we've extensively tested the type trait, we need to verify that we actually did say R in the implementation. And importantly, that future refactoring does not accidentally drop it. I can see that it is in the implementation, but this machinery is complicated enough and it gets refactored over time that we want to make sure that that R is there. And currently there's no coverage of that. So let's add a comment for this. It should be around the no except stuff. Right around here. I can say it would probably be the invoke R. Yeah, just trying to think like what line should I comment it on. This test coverage is great, but I think we need to cover one additional thing. The standard and the implementation here uses, and let's just copy because I'm lazy and I don't want to retype all the gibberish. If this will go away, please go away. Standard, we want invoke R, this one, uses is no throw invocable RV to examine the no except, yeah, that's a horrible word, to examine whether the return type conversion throws. It would be possible for a mistaken implementation or one damaged during refactoring to omit the R part. I think this should be as simple as verifying that plain invoke of a, let's just sketch out a const char star whatever no except is no except, but invoke R string is not no except because strings const char star, because the string const char star, I have a habit of writing the space here. It just looks better to me, even though plain format doesn't do that. More code base, because the string const char star constructor can throw exceptions. Okay. This test coverage is great, but I think we need to cover one additional thing. The standard and the implementation here uses is no throw invocable RV to determine whether the return type conversion throws. It would be possible for a mistaken implementation or one damaged during refactoring to omit the _R part. I think this should be as simple as verifying that plain invoke of a const char star whatever no except is no except, but invoke R string is not no except because the string const char star constructor can throw exceptions. Okay. Okay, that is it. I cannot think of anything else we'd want to test here. And no, this has not been implemented in lib66 yet, so we don't have any skipped tests there. There's no other like global tests that need to be added or modified when this is being added. All the existing Invoke machinery is not affected by this leaf. So I think that's good.
Stefan, if I
Yes.
could interrupt really quickly, I do have a question regarding the test. Oh, well, actually, two comments to make about the test.
Sure.
One is that I did not notice any test which exercises something like a, I guess, an object with.
You cut out there. You said, I guess, an object and then nothing.
Oh, right. For whatever reason, it muted me again. So if you have an object which mutates its internal state as it's being invoked, right? Like, since this is a perfectly forwarding interface, I would expect there to be some kind of test to verify, like, hey, the object on the other side, once it comes out of the invoked, was actually modified, right?
Yeah.
And
that's a reasonable thing. Yeah.
The other thing I didn't see was actually exercising the perfectly forwarding interface part of it. So, like, I would have expected to see a functor object which has two ref qualified operator parens. And, you know, one gets called depending on, you know, the value category. Well, not value category, because ref qualifiers aren't a value category. But I would have expected, like, a test that verifies one or the other gets called.
Yeah, that's a good question. We could forget the forwards there. I saw them in the code, but again, it could be damaged during refactoring. You're right that we should have that coverage. I definitely I tend to be a little bit lazy when I can see code there in the implementation, and I've got some heuristics that say this is liable to be damaged during refactoring, but this thing we couldn't possibly damage. Like, we would have to be completely asleep. But it is reasonable to have such coverage. We do have coverage for both of those things in plain invoke. The can I modify something persistent? I'm almost absolutely certain we have that, and we definitely have is the function object being called in a value category sensitive way. It seems reasonable to have a couple test cases of that here. So I'll add that. Thanks. Let me go add that at the bottom here. Okay. Mar suggests adding test coverage for a couple more cases, which are extensively exercised by the underlying invoke machinery. We just need to verify that nothing is being, that everything is being perfectly forwarded down to it. Number one is calling invoke R on a function object that updates its state should update. This is actually interesting because we perfectly forward it. So no copies are being made, even in theory. It really should update the original. Should update the original object, i.e. no copies are made and then dropped on the floor. Would be as simple as lambda with an init capture that increments a counter. Two, the function object and, or not function object, callable object. The callable object and its arguments should be perfectly forwarded. Let's see, would or could verify with a function object that has ref qualified operator paren overloads to sense the object's value category. And you could also make it templated on an argument type to verify that value category. Okay. hopefully that makes sense. Let's see, Cameron. Yep, that's right. Username suggests adding test coverage for a couple more cases, which are extensively exercised by the underlying invoke machinery. We just need to verify that everything is being perfectly forwarded down to it. 1, calling invoke R on a function object that updates its state should update the original object, i.e. no copies are made and then dropped on the floor. And here I'm specifically saying function object because pointers to members can't possibly update their own state. If they try to update the object, that's actually one of the object is being passed as an argument. Would be as simple as a lambda with an init capture that increments a counter. Callable object and its arguments should be perfectly forwarded. Could verify with a function object that has ref qualified operator parent overloads to sense the object's value category. And you could also make it templated on argument type to verify that value category. Does that capture the test you were looking for?
Yeah, perfect. Thanks.
Awesome. Yeah, thanks, Cameron. Really, really appreciate it. We are definitely trying to be more vigilant about testing. Our history in the STL is that we originally didn't really have any tests. Then we started adding just tests for like bugs that we fixed. This is like early on in my career. And then as we started implementing, more features, we started adding pretty extensive unit tests for features as we went along. So the more recently implemented stuff tends to be much more robustly tested. And now that we're moving into, the GitHub open source era, having like real extensive tests makes it in the long run much easier to contribute because you don't have to worry, oh, what if I broke this, subtle thing that's only going to show up when we actually ship this to users? If it just fails right there in our own test suites, not even like our open source test suites that are run with some delay because they're so large, that just makes it easier to make changes and refactor things more confidently. So spending a little bit extra time extensively testing stuff, like even if we think it's not going to find bugs, it makes it easier to make changes later on and also make sure that the compiler doesn't break or new compilers as we add support for them or new architectures don't regress stuff. Can't even count the number of cases where we wrote tests. They're testing like, what we consider to be blindingly obvious stuff, and they always passed until something about the environment changed, some new C++ rule or new compiler or new architecture, and only that, one obscure test and test stood, whatever, that was written, 5-7 years ago found it. So this coverage adds up, and if it doesn't take too long to write, then why not add it? Okay, so let us request changes. Okay. Let me double check. We got all the comments asking about. So what did we find? We got the constraint that should be by our conventions enable if t, renaming member function, being real nitpicky about the type, long int, commenting our preprocessor conditionals, probably simplifying is R value with just use is same v decal type. Covering what if the conversion throws, because every step of the process could throw. And then Cameron's suggestions of what if calling the function object updates its state, let's not make copies, and everything should be perfectly forwarded down. One test should be sufficient. We've got extensive tests elsewhere to make sure, yes, we actually get the const and the ref and all that. Okay. And in the implementation of Invoke, we actually did need to be real careful about that because all the stuff that manipulates function objects, which are things that are called with parenthesis, they could be objects of class type. So we got to be real careful about forwarding them down. We did that even before ref qualifiers became a thing in the core language, or before they were actually implemented, because I think we knew the feature was coming, but they just didn't exist in the compiler yet. Whenever we know that the callable object is in fact a pointer to member, at that point we just start passing it around by value because we don't, there's nothing that can sense whether it's a L value or R value. But we got to make sure we do that at the right time. We don't do it too early. Okay, I believe that is our code review. Does anybody have other questions about what we covered? Doesn't sound like it. So thanks everyone, and we'll see you next time.